Thanks for coming back for demo. So this is Joongun Park. I'm postdoctoral researcher under supervision of Professor Tuja Krishna. And I'm working on chakra and ASTRA-sim side and the entire torture in between there. So in this tutorial, the agenda is just showing how chakra can generate the traces or collect the traces and how ASTRA-sim can parse them into real result. So you can check our website here to get the more detailed information if you need it. So we have three parts. So first, we're gonna install and clone and install chakra and ASTRA-sim. In part one, we're gonna generate the traces with 4 different ways. And in part two, we're gonna use those traces to run the ASTRA-sim with various network setting or system configurations. So yeah, we provided a Docker environment on our GitHub, so you can download it from there. And if you want to change some code or if you need some modification for your specific purposes, you can get you can build this by your own way. So first, we can start from the cloning the tutorial repository. And since it's straightforward once, I just already did. And then you can go into here. So CD tutorials, micro 2024. And what you're gonna do next is clone repositories. And when you run clone repos, then you will see ASTRA-sim, ASTRA-sim demo and Chakra demo. And then what you're gonna do is Docker pulling the pre-built image and run in your own environment to avoid any conflicts or problems. Once you get in the Docker instance, you will see this path. And what you need to do is move to micro 2024 directory here. And then we're gonna run install chakra script. So this will basically clone the chakra and some modules and build in the Docker instance. Then you can also compile ASTRA-sim with just prepared script here. Compile ASTRA-sim.sh. Yeah. And it's simple. So in part one, we're gonna show like 4 different ways to collect the chakra traces. So first one, we're gonna show the simplest one using the chakra API. The second one, you can define the model with the text-based approach, so you can actually do without any real trace or real model. Third one, we provide a synthetic trace generator for end-to-end large language model simulation. So I will also show that, show this for you guys later. And at the last stage, I will show how we can actually collect the traces from actual PyTorch runs. So simple chakra execution trace can be manually made by using Chakra API. So you don't need to fully understand this, but what basically it does is making Chakra node and just encode the size of the communication, type of the communication, like here all reduce, and how big is the communication size, and the number here. So basically this Python code will make a single all-reduce node. So what you're gonna do is first go into Chakra demo, go into Chakra demo 1, and you will see generate all-reduce.py. And first I remove the existing one. And if I run Python 3 and this, then you will see all videos for 8 GPUs. So this is just single chakra node. So it will not give you, you might think it will not give you very meaningful result, but if you put this put this input to ASTRA-sim, then you can actually use ASTRA-sim's network backend and detailed simulation for all it use, which will show you later in this demo. There's another script here. This one will make a whole set of chakra node examples. So when you just run it, you'll see, sorry, I will remove the existing one. Yep, there is traces with all different set of collective communication. So like one communication send receive, all to all, or barrier can be encoded in chakra as well. And as you guys know, chakra has dependencies between chakra nodes. So we can also see an example with dependencies. Yeah, which will basically can be used for your simulation purposes. Yeah. And next thing we're going to do is based on the text-defined model. So in this case, model level parallelism with 6 layers and parallelization strategy, we're going to only use model parallelism in this case. And for each layer, we're going to do all gather, all reduce with the following data size. So let's go to demo 2 here. And you will see text workloads. So we already prepared some sets of predefined sets of text. So you can use other ones, but in this demo, I'll show MLP version only. So if you run demo2.sh, then you will have another directory called workloads. So if you go there, you will see 32 model level parallelism example, which can basically, I mean, you can use any arbitrary number for generating those traces. So when you take a look into this script, chakra converter will convert the text workloads into traces with 32 MPUs. And the result would be shown like this. So Chakra has a internal module called visualizer. There's also script for visualizer. If you run this, you will see a PDF file is generated. And if you just bring it to your local machine to see what's in there, you will see in 4FS, we do all gather because it's model parallel. And there are at most, yeah. And as you can see, there's two branches of dependencies. So on your right side, it's compute node, and on your left side, it's communication node. So as sir, you asked, compute node and communication node can be overlapped because these two operations do not have any dependencies. So yeah, this one is this one is the one we used before. And now we can actually have more sophisticated way to synthesize the traces, so-called STG. So this STG can model multiple parallelism strategies, including data parallel, tensor parallel, pipeline parallel, and sequence parallel. Also, it has configuration file for transformer layers. So by giving any numbers there, you can see you can generate any arbitrary transformer traces. So in order to run this, you can go what you want to do is go in demo 3 and just run it. So when you see into the detail of this trace, it specifies number of data parallel, tensor parallel S2, pipeline parallel S2, and we have specific communication group setting we get those information as an input. And based on those configuration files, STG can generate 8 GPUs trace here. And next, so now we want to collect the real traces from the actual run from PyTorch. We use as PyTorch's profiler to get those 2 different traces as we got the information from the earlier demo. So in order to capture the model activities, we register 2 observer, the start of the trace and end of the trace. So we don't want to go into detail because it's already explained, but this is how we do. And if you run the PyTorch, you will see you will get 2 different traces, 2 kind of traces. One is host, the other one is device. So since it will take some time, let me run a example earlier. So this is cluster. So just let me get a job from the cluster. So what this script does is acquiring 2 GPUs in that cluster. It seems cluster is quite busy, which is always happening during the demo. Yeah. So what you're gonna do next once we can get the traces is run the actual PyTorch model. In this case, it's ResNet. We're gonna have host trace, which includes CPU ops and dependency information. And we're gonna have device traces, which includes both CPU and GPU ops and timing information. As Taekyung explained, by having a merge trace of both information, we can have actually more detailed trace than PyTorch provides by default. So I already put the collected traces in demo 4. So when you go into PyTorch traces, there is 2 device traces and 2 host traces. And what you're gonna do next is run merge.sh. So in merge.sh, you will match 2 different traces with the various index. For example, we can use the name of the operation. We can use the timing information of those traces. So it's lots of heuristic, but detailed optimizations are there. And next, then we'll see there is a JSON files came out, which we call host device trace. And what you're gonna do is this JSON file, convert this JSON file to protobuf files, which we can be used to ASTRA-sim or other simulators. So also, this conversion process does not only do format conversion. What it does in detail is it first remove all the force dependencies between the operations. So for example, obviously cycle dependencies will not gonna be happen if we collect the traces. The other one is we refine the traces to have very essential data, what we are going to use in the simulators later. Those are defined by our chakra schema, so which have so current version is 0.0.4, but if you need any more data, any more attributes to have to contain or to encode it in the traces, you can basically define and use it by own your purposes. Yep. And after the conversion, you'll have two ET files. Yeah. So this is the flow chart on your right side is the for how we done during this session. So we first merged it and converted it. So now it's part two. So running ASTRA-sim with various configurations. Since we have plenty of, 4 different ways of generating input, now we should run it on the simulator we have. So in system layer, in ASTRA-sim supports several, more than 4 and 5 collective algorithm, even for a single dimension topology. So here, if the net topology is fully connected, you can maybe use direct collective communication, which will just send the data all the way at the same time. And we have ring topology and ring collective algorithm, which will share the data across the in a circular way. And we have halving doubling, which is known for good at switch topologies. And as you can see, first node 0 and node 1 share the data, and then while 2 and 3 share the data at the moment. Also, and then in the next stage, 0 and 2 will share the data, and 1 and 3 share the data. So in order to configure this in ASTRA-sim, first you can open demo 1, system definition file. So let's go to the terminal again. So first thing we want to do is going to make sure you are in the ASTRA-sim demo. And then let's go into demo 1. So there will be 2 different network setup. Collective communication algorithm setup. So in one is using direct algorithm for all reduce, all getter, reduce scatter, all to all. But if you want, you can use all reduce for with direct algorithm, but all getter with ring algorithm. So let's run the script here. Then you'll see how long does it take for running all reduce as we generated at the first demo in Chakra. It's a single operation. So as there is no compute operation, exposed communication time will be exactly the same with the time spent on the all reduce itself. And if we see the second script, it will run fully connected topology. It will use fully connected topology and uses ring all reduce implementation. So it will show the result again. And so by changing the collective algorithm in ASTRA-sim, you can actually evaluate your system without changing the actual code. So it will be really quick and fast. So let's get into the some complex scenarios. So in the network, so now in this demo, we are going to modeling more complex scenario with 32 GPUs, and it will have 4 different DGX node. So each node will be within a DGX, it will be connected with switch. And even among the DGX, they will be connected with switch. So we can give a topology as a 2-dimensional switch topology. And the MPUs count will be like within a node, we have 8 GPUs. And we have 4 DGX. And within a DGX node, all those GPUs are connected with NVLink, which has a unidirectional bandwidth as 450 gigabyte per second. So we're going to put that here. And for InfiniBand, which is the network connection between among the DGX. So I'm talking about not like DGX superpod. So it has heterogeneity in network connection. So we can use that number for evaluating this system, and make sure the MPU, the dimension matches. So within a DGX, you're going to have 450 gigabyte per second, while among the DGX, you're going to have 50 gigabyte per second network bandwidth. And what you're going to do next is we're going to give the algorithm for collective communication. So we'll use halving doubling in this case, given that the topology is switch and switch. Same as well, we put like we will specify 2 collective algorithm here, but basically you can set this ring halving doubling or halving doubling ring. Same as the earlier demo. Let's go to demo 2. And if you just run 2-1 sh, you will see 32 MPUs are running in our simulator. So if you take a look into this script, you will see how this is DGX setting, and you can change any values in this file for your own purpose. So next we'll see another model. So we're gonna do modeling for TPU V4. So it has 3D torus interconnect topology with 32 TPUs. And as you can see on your right side, it has 2x4x4 topology. And since it's torus, we'll put like ring, ring, ring for this one. And MPU counts will be 2x4x4. And all the interconnects between the GPUs will show 50, not GPUs, TPUs will show 50 gigabyte per second unidirectional bandwidth. So same as before, we're gonna give here the collective communication algorithm. In this case, we use ring, ring, ring for all 4 collective communications. Yep. So it's simple and fast. So you can scale out the topology even with 4D or 5D if you want, and you can change the latency of the link or bandwidth of the link, and so on. So the thing is so we have NAT3 network bandwidth. So in previous demo, we used analytical backend, but using NAT3 can be also applicable. But in this demo, because it takes longer time than analytical modeling, we're not gonna show the demo in detail. Yeah, but the way we do is basically the same. Just you can convert the name as NF3, and the concept of logical tuples can be adopted here as as Williams' demo has. So yeah, that's end of the demo.